I hope we will have interesting discussions after the talk. So actually, first, thanks for the invitation. I think the subject and the topic are quite interesting and still mobilizing the scientific and research community. So the outline of my talk is going to be, first of all, trying to get a brief understanding of why considering machine learning for networks in the networking context. Then I will shed a light into the context and applicability of what might be seen as the conventional data analysis and machine learning methods. Explain why actually, what are the root causes that these problems are still being hard to solve. And then try to bring some elements of answers why actually algorithmic methods like neural networks, how they could address at least some of them, and then draw some conclusions and perspectives. So let's start with the introduction. Why considering machine learning at first place? So, well, I don't think I need to go into much details about what we mean by machine learning, but at least from my side, I see this as a class of algorithms that helps in discovering or uncovering relations between variables of a system. So that being input, output, or even latent variables from direct observations of that systems. And so, well, actually, the reasoning behind was always, if you look at the application fields we know nowadays, being NLP, natural language processing, speech recognition, or object recognition in computer vision, the question has always been, is there actually an equivalence or a similarity between these problems and those that are going to be faced in the networking context? And so, well, indeed, a priori, you can identify 5 major, I would say, criteria of similarity between these problems. They are of complex nature. Events cannot be well characterized, even when numerous examples are being available. There are hidden relationships and correlation trends in the data, in the events of data that are captured from certain events you want to analyze. You have changing environments. I will come back to this. Changing conditions over time, being at the routing systems, at the traffic level, or even actually at the user expectation or behavior level. You typically, I would say that has to be reconsidered, large data sets to be considered. So that actually human handling would be difficult to consider, and environments are highly evolutive. New events are constantly detected and discovered. So why considering machine learning? I come back here to the work that was done actually in our initiatives that started now in 2000 and between 5 and 7, so it's about 15 years ago. It was the idea that we would be able to bring a common framework for addressing, I would say, key networking challenges. Key networking challenges at that time was traffic and congestion control, routing and resilience, and security. And I have summarized actually what are the key, I would say, internet challenges. And so based on that, the question was, can we identify clear use cases that would be on it in order to overcome the major architectural limits being at the protocol or design levels of the internet? And then you have, and I will mention them once so that people have a good picture about what was the target, the objective. Could we have actually good telemetry and metrology, I would say, techniques, including probe calibration and placement, good traffic analysis and forecasting, prediction, and traffic control, I would say, systems, enable early network congestion detection and prediction. Do we have a good understanding about how the forwarding path quality is behaving, the bandwidth delay product, and bandwidth delay packet loss, I would say, analysis, prediction and control, failure and instability detection, identification, and prediction, being both at the forwarding, also at the routing level, automated root cause analysis so that you can have a good understanding about which actions need to be taken. And then finally, security. All those are related to security, intrusion, anomaly detection, identification, and prediction. And at that time, actually, the idea was, if you take a node, it has a forwarding and a control component, can you add a machine learning engine component to it? And that was the idea. That was the base idea. Are these nodes going to go to the next level of evolution, like you would add a level about being a machine learning engine? That was the idea. Well, what we faced was, and this is the perspective, this context and applicability of conventional DA and data analysis and machine learning methods made it such that actually the goal was much more difficult to achieve than expected initially. But I want first to refocus a bit the discussion here. if you take this as from a pure networking perspective, the goal is actually not actually at all about how the application layer behaves or all the file layers behave. It's really to have machine learning being used as a transformative mechanism for the forwarding and control processes. That was the goal. And of course, actually, you have, and you had many talks this morning that were discussing about what is the role of the network management, but the perspective was not to have the network management correcting the forwarding and control, it was the other way around. Is it, can machine learning enhance forwarding and control in order to make those networks operating better than what we know? That was the goal of those initiatives. Well, when we speak about analytics, and I will go to, there are three broad levels of applicability. And probably people have heard about those. It's the descriptive level, the predictive level, and the prescriptive level. The descriptive level is always to answer the question, what has happened? And even if you, that's purely actually use actually the processing of the data in order to have a good understanding about what has happened in my system. Then in terms of techniques, what you have is qualitative or quantitative data analysis techniques, patterns, event detection and recognition, summarizing key feature extraction and classification, but also inverse modeling. And typically associated to this, you have the explanatory level, the diagnostic, the root cause analysis, why it has happened. Then next level, can someone close the door, please? There is noise. Then there is a predictive level. What might happen? What's likely to happen in my system, knowing actually what I have been modeling. So here the techniques is statistical modeling methods like regression analysis, time series analysis, patterns or event prediction, predictive forwarding modeling. And typically you have to consider this as being exploratory by nature. You try to explore what might happen into your system. And then the last level, which is associated more to the decision process, which is prescriptive. Which decision and action should be taken and what should be done. And then typically what you have there are techniques is structured learning, math programming models to optimize a set of decisions for directing a given objective that you want to achieve or for achieving desired outcomes. So the conventional methods, and I go back to this idea that you set your domain objective and solve it here. In this case, it was a big challenge of the internet networking system. And then the question is, you are dealing with descriptive and predictive methods in the context of data analysis and typically in statistical data modeling methods. And then what you understand is, well, there is a single paradigm which is driving all this. It is, you assume that your data is being generated by a stochastic model where the response actually corresponds to a transformation of predictor variables, noise, and parameters. And all methods are parametric. You need to learn the parameters of your system to have an idea about how to model that function. And so what was our problem is, whatever the type of problem we had at first glance, it was always to estimate parameters in order to have an estimation of a function that transposes actually the response of that system. The problem that was there is, you can imagine how many actually type of events and phenomena you have. You take traffic analysis, you take traffic flows, you have for each of them determine which parameters are characterizing actually that flow and associated to it is processing. That was becoming actually, that explains why it's going to be challenges, because you need to have a parametric description of your phenomena. Of course, there was the link towards the predictive and the prescriptive methods that came towards it, in particular the use of machine learning using the inductive, it's typically by induction, we learn from experience. So typically what we mean learning by induction is from examples of your system, X, Y, you have actually an approximating function, F, that explains actually the output of your Y being equal to F of X. So, and once you have that approximation being in place, you can start and make deduction. So you have new points coming in, you can actually compute the value of that function. That's actually the key goal of machine learning. You go from example, you have an approximating function by induction, and then you derive deductions. So how did it go? Of course, then he was trying to make those, I would say, blending of techniques valuable for solving these challenges. And then probably, I don't know how much time, already 20 minutes. Half an hour, ça va. So I want again to explain actually how this data modeling cycle behaves. From the data collection, data pre-processing side, you can have some stages on exploratory data analysis, But then I would say the key task is always oriented towards the modeling and the algorithmic. And if you take actually these data modeling methods, as we knew them, those conventional ones, they were based on estimating the parameters of a function. And actually, this estimation, I would say, type of task was also becoming our bottleneck. Then you have all the model validations that you can come afterwards and center on parameter estimations, of course, the confidence interval that you can draw, and all the statistical tests, like goodness of fits, and validation test, out of sample order test, cross validation, missing data outliers, sensitivity, and so forth. Then the next part, which was typically left a bit behind always, the model interpretability. How can I interpret my model? And then you have typically 3 levels of studies: the stability, the robustness of your model, its generalizability, and its feature attribution. So I will switch now a bit to explain in that context what was the paradigmatic approach to be used for machine learning, in particular for supervised learning by experience. You have a set of data, and what you do is you have a segmentation that can be tunable with a training set and a testing set. And typically what you have a learner which takes actually your labeled input pairs xy and extracts actually the value hf of x, which hf is an hypothesis that you draw on the targeted function that you want to model. And actually you have only a knowledge about that function f at the point x because you know the values y. You test actually the quality of that hypothesis, so you have actually an informative or predictive model hf and a training error. And if it's satisfactory enough, you transfer actually that hypothesis to a performer that actually is able to then determine how good you are at testing or at predicting actually typically your values y by having a good estimation about the testing error, which is typically then measured instead of having the loss between hf of x and against y is hf of x prime, y prime here, because this is how I've segmented my data set. And then you have an approximation of the target functions out of this learned model. This framework actually typically also works for semi-supervised learning, where the major difference is that typically you run with a limited labeled data set, and so what you do is you derive assumptions from unlabeled data in order to refine your hypothesis space H. So to give that example here, and I want to make a highlight, not in order to explain how the learner is actually being designed, but what characterizes a learner. It's not just about the training algorithm like you hear today. It's the family of candidate models, so the hypothesis space for which you draw actually a small h of f. The training, of course, is going to be not just an optimization with the combination of an approximation, an estimation, and optimization algorithm, and then the quality criteria and metrics or measure for the model that you're going to learn. And I think that's important. It's not only centered toward the training. It's about the combination of the candidate models you have, the training algorithmic you're using, the quality criteria you have. And then actually the procedure is the one that you might be imagining, that out of your labeled data set xy, you extract actually the value of the hypothesis over those points in order to determine it's a classification or linear regression model, actually, where the basic difference is that in the classification case, you have symbolic output, and the linear regression model, you have numeric output. So this being said, this is how the distinction can be seen between the data modeling cycle and the machine learning cycle. Is that the major difference is that you don't make estimation, you do approximation of the target function. So technically speaking, this is the major difference. Of course, what does happen is you don't have any more model validation. You need now to have a model validation and verification technique. You need to verify that what has been learned makes actually is interpretable in terms of the process through which you have been deriving these relations. I'm speaking about this verification. The estimation error is then being derived by this, by having a good understanding about the approximation bias or sample error variance, bias variance trade-off that you can have, and the various measure of accuracy you can have in terms of precision and trueness, closeness of the actual value that you want to model. Having laid out a bit where we stand, I would say up to the neural network algorithmic modeling method came into the loop, I will explain what was our understanding about the root causes of the complexity of networking problems. The first one is the statistical properties of the data. We are being using actually machine learning supervised or not, you learn from experience. So indeed, neural network or not, you can be agnostic to the data generation mechanism, but you cannot be agnostic to the data properties themselves. The second point is most of the methods were more explanatory or so informative than predictive. We were better at explaining the past, what has happened, than able to predict what would occur. So, and the last point is the complexity of the network learning task. Typically, they are not atomic in the sense that you have, as I said, to take into account the trade-off between the learning error, the bias of the model, and generalization error. But you have also actually all these problematic in terms of the lack of automated or online training techniques. So even if you assume, and the talk of this morning was also, even if you have an end-to-end model from the data feature extraction up to classification and regression, you still involve lots of sequences of domain knowledge or human intervention. And finally, there was a key question that were falling back to us, which was related to the cost-gain ratio versus actually the objectives that were reached by putting in place all these techniques. And the example that I will show here was extracted out of that project. And actually what was the purpose was rather simple. If you have a shared risk in a network, which means links that can fail simultaneously, you will do sequential recomputation of your shortest path tree in a linked state environment. And the perspective was, how can we actually derive links that belong to the same shared risk group in order to avoid this subsequent recomputation? Extremely easy to even formalize mathematically, if you want, in terms of rival process of linked state advertisements. So it was just, you detect that the first LSA arrived, and you know that that LSA linked state advertisement belongs to a larger group, so that you can take all of them and prune all these elements from the database and do the computation. Extremely easy. The problem was, even if you take this very straightforward case and you want to integrate it within an OSPF stack, you already require relatively complex integration and interfacing with the routing protocol stack itself. The routing path computation is not changed, but you need to have an additional linked state information storage and update technique. You need to have different linked state information processing. You need to store actually all these shared risk groups. So what I wanted to highlight here, that collocated management plane or not management plane, enhancing the routing plane impacts actually its design. So do not believe that this is going to be seamless. You are going to have a different way of processing linked state updates if you want to implement these kind of use cases. And all of them that will, I would say, rely on linked state updates will follow a similar type of I would say, design impact on the routing stack. Another point is, people, if you get in touch the first time in your life with the machine learning, you will say, know your data. And my answer is yes, indeed. Because actually, what has happened is they provide guarantee in two cases. Data IID and the linear regression model can be modeled in that way. Then actually, all what is in place today delivers you guaranteed solution. If your data is not IID, so actually, Barry ID is not the data being generated by a common memory-less generative process. Or you can see this also as big independent draws from the same probability distribution. Then actually, you can guarantee that in that case, the data distribution at training time will be the same as the data distribution at testing and generalization time. Those are the conditions to which they guarantee quality of the learned model. And then typically, another, I would say, core assumption that you have is that the data sets have to be such that if you want to model the response of the system as a linear regression, the errors have to be uncorrelated, have a zero mean, so verify the exoneity assumption, have a mean of equal variance. Typically, the process has to be homoscedastic. This has a huge impact, because if one of these assumptions is not being verified, you cannot apply the classical, I would say, regression technique which are being used, and basing least square, you need to go to weighted least square. If the error are not homoscedastic but heteroscedastic, then you have to move towards weighted least square, and they might possibly give you an answer. And if your error is being correlated, and you have unequal variance, then you need to go to generalized least square or iterative reweighted least square methods. So what I'm saying is the classical techniques that you find in libraries that are provable when those assumptions are being verified, they don't find applicability in our environment. In particular, and this is where I wanted to end, in our environment, the data are non-IID. They are showing coupling relationship, they are not independent, and they are heterogeneous, they are not identical. So you may say, I don't mind, my neural network will find an answer. The response to this is, you will get actually very poor generalization capabilities. And you may learn something that is completely wrong, basically. And it's a bit what I wanted to say. It's a critical assumption. ID assumption is a critical assumption in statistics, entropy estimation, but also machine learning. May induce bias, incompleteness, performance degradation. And it's particularly important in our environment, by the way, because you are working in decentralized data environments. So that you need to, the IIDness is associated with the fact that we are in distributed systems. So when actually you see that a collection of random is IID, well, if each of the samples have same probability distribution as every other sample, and all samples are mutually independent. So if you don't want to remember or have a good formal, I would say, understanding about the meaning of the definition, just take these two, I would say, graphs here. On the left side, you see an ID behavior. On the right-hand side, a non-ID one. You have clearly a shift about the distribution of the data over time. Unfortunately, there is, I would say yes, but we can test if our data is RID. Well, that's an extremely difficult task because to test that actually IDness, in particular independence, is far from being a trivial statistical task. Two things that people have to remember, because I think I will try to shift a bit farther on the next step. Stationarity doesn't imply IIDness, and white noise doesn't imply IIDness. Only in one case, you can assume that if you have a Gaussian white noise, then your data will be IID. But I want to remember something to people here. It's not a restriction about the type of process that you want to model. It is about the information about the system that you want to model and how this data is being observed. And I think that's a major difference. It's not restrictive at all in terms of models that you want to learn. It is about the way that you are actually taking the draws and the observation out of your system. So the question has been, and could algorithmic methods address some of those challenges? And I think that's probably going to be what you may call the second generation of research in terms of, or third generation of applying machine learning to networking problems. What do we mean? Well, basically, actually, we've centered specifically now on neural networks, because in the data analysis part, the question is not just relying on data modeling methods, but also on these algorithmic ones. And as I said before, typically what you aim at doing is to find the function such that f of x equal y. So you can explain actually, or I would say approximate your output. And I will come to this at the end too, the question becomes, this predictive step now being algorithmic by nature, you may also facilitate the inception of machine learning algorithmic, in particular if you rely on an inductive paradigm. So let us see how this could work. And I will come to this and explain actually what is the shift in the class of techniques that we have. If I want to summarize what I said just before, all statistical modeling methods were focused on solving regression problems by estimating the parameters. And this is typically actually the process that was put in place. And actually, you were then taking decisions on estimated relationship between, based on statistical tests like coefficient of determination, cross-validation, and so forth. But actually, a good fit, even if your coefficient of determination is close to 1, doesn't mean good prediction. And that is a key element. Good models do not necessarily mean that you have good explanatory capabilities, doesn't mean that you have good predictive capabilities. In particular, if you have an evolving dynamic system, you are dealing with non-stationary processors, and this independently that your function f is being approximated by your neural network. So the shift was to look a bit, and this was historical here, how physics was doing things, because actually there is a more general class of problems that you can solve, these inverse problems. But this is typically when you have a physical understanding about how the process behaves. So the data-driven method, and this was really the shift of neural network, is to enable actually to have a direct application of direct algorithmic methods for the solving of inverse problems. So you have pairs of observation and model parameters, and from there you can actually, the neural networks, actually what it does, it approximates the inverse function itself. And this was the key driver towards having a good understanding about which model characterizes your parameter, and then afterwards you can predict actually the value y predicted here out of the system. So instead of actually deriving everything on estimation, the goal was to have a good approximation of the function itself in order to have a good approximation and estimation errors, and then of course predictive capabilities. So, well, how we do this? I will skip to that slide because probably is a bit too detailed. The main challenges in neural networks, and when we started with this, because actually we were trying to exploit neural networks for doing this, was first of all, you can see these challenges in neural networks as being at 4 levels. The first one is the neural networks, what they are relying on is this universal approximation theorem. We say that you can approximate, a neural network can approximate any class of functions. But actually this theorem only relies on it actually copes with the representation capability of that network. It doesn't address actually a wider learnability of these parameters. There was all this question about how to design the neural network itself. How many layers do you need and how many units per layer you need in order to efficiently represent that function? So the trade-off depth versus width in neural networks. And then all the research which are related to neural networks, structural search and data-driven methods. Then there's all the training, and all the training we felt into many challenges because actually we are not anymore in a convex domain, but in a non-convex domain. So typically the training of neural network is about minimizing non-convex loss functions over non-convex sets. So that makes actually the training rather challenging on its own. And then the generalization. And I believe that there, we are still at a major challenge in terms of what statistical learning theory can tell us. We don't have complexity measures from statistical learning which can explain, which enables us to explain the generalization capabilities of neural networks. It's a pity. Why? Well, actually, you have always to remember one thing. I heard this morning that what is important is training. I fully disagree. What is important is generalization. You can have low training error, low testing error, I don't mind. What's important is generalization error. It is actually, a learned model shall yield good generalization properties on never seen before data from the same experiment, not only minimizing training and testing error. The point is that statistical learning theory is enabled to explain actually the generalization capabilities we are seeing out of neural networks. In particular, in what we call the overparameterized, I would say, regime, where the number of parameters of the neural network is higher than the number of data points we have. Because actually SLT would tell you that normally you should have poor generalization capabilities because you just learn noise. In fact, in neural networks, you still have satisfactory generalization capabilities in that regime, which doesn't mean the best. I would like to put a highlight that satisfactory doesn't mean best, for sure, because actually you still exhibit a small gap between training and testing error. Not explainable by SLT. And the existing theories of complexity we have struggled to explain actually the generalization properties of neural networks. So, well, the state of the art in terms of knowledge is in the classical SLT, you have a trade-off between bias and variance, or underfitting and overfitting. The perception that happens nowadays in neural networks is that actually there is a bifurcation point where you are running in 2 different regimes. And this is one of the reasons why I have many statistical physicists looking at it, because if it is a bifurcation, it means that actually there is a change of phase in the working of the system. So, well, the question that was posed, and I will take it more a practical perspective, where neural network can help us in solving certain of the problems we have in networking. And I took actually one of the major basic case, time series analysis and forecasting. And I tried to see, is actually neural network going to be better than learning the parameters of a Farima time series model that I was doing in the Z-code project, where for each flow I had to learn 5 parameters and update them at each count. That's the goal. To look at what is the advantage in moving towards algorithmic methods more than statistical modeling methods for traffic flows and their prediction. Take this. So a time series, what it is, just to have the point very clear, it's a sequence of discrete time data where you have actually a representation of a series of successively equally spaced point in time, represented by these sets. And you have typically three major, I would say, type of task or goals in there. It's their analysis, so extract meaningful statistics or the characteristics of the data. Modeling, model selection and parameter estimation, or time series forecasting, using a learned model to predict future values based on previously observed one. The point is, all these techniques are valid, very well understood, if actually the stationarity and mixing assumptions are being verified. But they are often, these assumptions often do not hold for network processes and particular traffic. So they require data pre-processing. What I mean by requiring data pre-processing is, and I will give this example, you typically need the risk grading of your data. You take your x min, x max, you put them in a space minus 1 plus 1. And you want to stabilize the variance. And one technique to stabilize the variance is to use a Fisher transform. So typically this is a technique to be used in order to approximate variance stabilizing, well, it's an approximate variance stabilizing transform operation that you do that allows actually to transform the data following any probability distribution into approximately a Gaussian distribution. The good point about this transformation is also reduce the skewness. And skewness is a mean for testing how IIDness in your data. If your skewness is high, your IIDness is going to be high. So it's always also a mean for reducing the skewness that you're observing in your data set. And then this transformation, which consists in taking the arctangent in public of that points on the initial original time series. And typically what you have, if you have this time series, this is the density that you can compute out of it. Then as part of the data pre-processing, well, typically what you have is you need to take online integer or fractional differencing so that you go from a non-stationary to a stationary process description. And typically one of the methods which is classically used is to start with the first order differencing. Why are we doing this? Because actually you are stabilizing the mean by moving the changes in the level of the time series, and therefore we can actually eliminate or reduce the linear trend and seasonality that we might be observing. This also increases actually the predictability that we can see underneath. What I mean by predictability is not a word, it's a test. Because actually what you can always do in a time series is to test the Hurst exponent of your time that you can obtain. So if you have a test of the Hurst, to test the value of the Hurst exponent of your time series, if it's close to 0.5, you are all close to a random walk. If you're close to 1, it means that you have a long-range dependence as part of the data process. So there is something which is predictable out of your data. I want to say something. If your process is a random walk, you can do whatever technique you can. There is nothing to be predicted. It's 0.5. And the Hurst exponent equals that value. Remember this. And so the perspective was to try and see, is there something that we could do easily? Because actually the neural networks, the common understanding is you need to use a very large neural network in order to be able to extract values out of, output values out of the input that you are injecting. And so we tried experiments like I'm depicting here. You take a data set, you have n data points. So you segment it in a trailing data set and a testing set. And then for each of those sets, you are segmenting them in a window size step of 10 count and one predicted value, or one. And a forecast. And we want to have a good understanding about the neural network that we want to put in place. So what we did was we computed the degrees of freedom in the data set using this formula and dimension a recurrent neural network, because in time series analysis, recurrent neural networks makes actually sense. It's a sequential data that we want to analyze. And we have an estimate of the number of hidden neurons by dividing actually the number of data points by this denominator 8 times 10 plus 1. 10 being the size of the window step, and out being the number of outputs that I want out of my RNN. And then actually the perspective was to use in parallel 3 very basic RNN models, each time taking this window of 10 and trying to outputting one value at the next count. And we tried, and we test here 3 models. And the first one takes an LSTM, long short-term memory RNN type with a soft sign, and a dense layer with a soft sign. Activation function. Model 2, again, a soft sign LSTM, and a dense layer being a soft plus. And actually, those are just a soft sign and soft are actually smooth variants about hyperbolic tangent and sigmoid functions. That's the only difference. And the third model that was able, in that case, to capture the spikes that you might be observing in the time series. What I want to highlight is we didn't have lots of parameters in our data series. It was about 400, 500 total parameters that were trainable. And actually, we tried to determine how predictable is all the data points of that time series. And we obtained, actually, by minimizing the loss among the three different models, a predicted value that was showing a cumulative error of about 10 exponent to the -5. So that's extremely interesting, because actually by having a decomposition of typically what you might be considering of a very complex I would say process, and having three very well-specified RNN recurrent neural networks, you could actually identify patterns around the traffic that you can easily predict. I think that was, and we projected this by taking data series, time series, injecting actually in them, removing certain values, and then playing them and determining how far we were able to predict actually the traffic that was coming, the flow prediction that were obtained out of them. And this is typically what you can obtain. So you see that this kind of model is able actually to predict the occurrence of certain spikes that may be observed in the traffic. And you can go even one step beyond. You can say, I don't want necessarily to throw all my, I would say, time series and run them in parallel. What I could do is automate the classification of these time series by extracting their statistical properties, redirect them to the right or a subset of RNNs in order to have, and then there a combination to get a filled time series coming at the end. So, well, this is to show an example. The example is exactly telling you that compared to what we used to have a decade ago in analyzing time series by classical statistical methods, where for each flow we had to design and fit a Farima model, a Farima-Gersh model, tune the parameters, update the parameters. Indeed, algorithmic modeling methods enables us now to go one step beyond that, and even not necessarily by bringing large, very two layers, hidden units, neural networks that you can use to perform online traffic analysis. I think that's a key message here. I wanted to draw also here what might be seen behind that, behind this, I would say, transition that I see from centralized training, centralized inference, and the use of these techniques for distributed training and distributed inference. And I think that would be a nice way to conclude this also. Typically, the main criteria that you have of people doing centralized training and inference is robusting and low generalization error. While if you want to go in a distributed training, different inference context, is going to be fast adaptation of the model. So keep them simple, as I was trying to show. Fast reconvergence time, but also acceptable accuracy level. Because I can be very fast and give you a junk answer, but you won't be fast and good at the same time. That's a factor. We are not decreasing the quality and the accuracy or the precision of the answer that we want out of our neural networks. What I can tell you is the downsizing of what runs today in data centers towards distributed system is not going to work, because their technique is to increase the model complexity in order to compensate for the lack of performance of the current methods using neural networks. So the downsizing this is not going to work for distributed systems. What you need to keep in mind is the label sample size is a dependent variable in a centralized system, while it is a constraint in distributed system. We have to operate on a limited labeled data set. So the key aspect for us is to go and determine actually the downtime. Can we decrease the approximation, estimation, optimization time while keeping the trade-off computational complexity versus accuracy trade-off at a good, I would say, level? That's the key for in terms of technical or numerical method challenge. The other one is to acknowledge that we are running in different environments than what the conventional systems are being running. They have full control of their data sources, while we only have a partial control of our data sources. And in particular, they are non-NID. They have labeled data sets. They can afford to whatever supervised learning task they can. They can learn from their model. we have many unlabeled data sets, and actually if you want to have labeling, we need to have well-defined objectives, because the labeling is a way of encoding the value of an objective function. That's the point. They have large data set, as I said. The label sample size can be a variable that they can do for their site. It's a constraint in our case. They can afford to run offline, basically, on batch or near real time. So the training time is independent of the data arrival process. In the systems like we have, we need to run online, meaning near real time, or process online the streams themselves. So we have actually a data arrival time process constraint, which constrains actually the retraining and adaptation time. Their tasks are often analysis-oriented, meaning that they are in a global mid-long-term target, and they are descriptive, explanatory, or predictive at best. In networking system, if you want to take something out of this, we need to be a local, or I would say a shorter midterm, and be predictive and prescriptive. What we want to have is a change of decision of the network, or the network decisions. That's probably what I have for this part. Typically, there is another challenge, of course, and this is more for the neural network, I would say, community, which is, I spoke that there were still statistical data modeling methods and neural networks. One of the big, I would say, goal of neural network is to be able to be the methods that are going to be applicable in data analysis and in the machine learning context. Of course, the methods might be different, but this is typically something that you have to keep in mind. Neural networks start to have more than what they were initially being designed for in terms of, I would say, analytics targets. And if you want, how much time have I got? 2 minutes, 3 minutes? 10 minutes? 5. Well, okay, so I will make an average. 5. I still, and I strongly believe that before moving forward into this fundamental question, there is one critical aspect. I strongly believe that machine learning will even adapt in order to have the right, or possibly, I would say, satisfactory answer to those goals. But the networking community has to set its functional and performance objective first, not only from the network, from the network manager or maintenance perspective, and certainly beyond automation and acceleration of what they can do. Because I see many of the cases that are only about automating and accelerating. That's not, you're not taking over the best of what you would expect out of machine learning. Unfortunately, machine learning is still not able to determine what's going to be the network objective of the objectives of the domain to which it applies. Well, I think we can stop here for the talk. I have a couple of announcements so people can read them if you want to participate to conferences where actually there are sessions dedicated to advances in mathematical optimization for machine learning at Europe, iForce, and MATOPT in Belgium. Thank you very much for your attention, and open for questions.
Thank you, Dimitri. So, do you have questions for Dimitri?
Thanks, Dimitri, for this insightful analysis of where we stand. I noticed in your presentation that, for me, it seems like a big issue on this IID-ness of the data. How do you think we can overcome that in our the applicability for network environment? How we can take that better into account for the design of the model?
You will not. Okay. You will not change the nature of the IID-ness of the properties of the data. You will adapt your methods, and that is the challenge. And this is what I wanted to say. I will come back to that slide one moment, because actually people are underestimating. It is not because iterative reweighted least square exists that it's easy to use. It starts to be also a domain knowledge to make the method executable. Weighted least squares. You need to know the weights. How do you know the weights? The problem of knowing the weight becomes more difficult than what you want to solve. This is a bit what people are underestimating is, and I believe that was also, where is this slide now? Here. The question is, the nature of it's inherent to the environment you are. You are in a distributed environment. Your data sources will have data generative process. You have different TCP connections going in, or different classes of traffic coming in your system. So the problem becomes, whether advancing these methods is going to be a prerequisite in order to make advances actually in networking. And I think they will advance in parallel because the environment that networking is experiencing is rather very specific. It is the larger distributed system that you have. Do you think that anyone else is going to do it for you? No, you have to invest in methods in order to have advances and deal with non-ideas or methods of transforming the data. Stationarization of time series analysis was a case that we found where we were exploiting actually different classes of transform and differentiation, fractional differentiation, not only integer differentiation, because that was a big, I would say, a big concern even 10 years ago in terms of computational capabilities that we had on each node. But this is the way that you are advancing. You are bringing more complex use cases and the methods are not ready, so you are advancing the method. Do not think that the methods would be ready to use for the cases you have. That doesn't exist, in particular in the complex environments that networks, distributed systems define. I think that's the message. The message is you are not going to have methods which are directly reusable, in particular due to the, I would say, the complexity or the characteristic and the properties of the environment that the internet defines, actually. That's the point. I must say that I'm also a bit, this is where I think there is a biased message when you have people presenting, yes, it works, yes, what does work and up to which extent. So indeed, if you have very basic formulations of your problem and you're eliminating actually what makes your extraction of information or hidden relation and you reduce everything to certain statistical analysis, yes, indeed, it works. If you want to go into this kind of more elaborated analysis of what needs to be done and how it has to be applied, of course, then you have to question weighted least squares is going to work in my case. Generalized least squares work in my case. And I've barely seen papers in networking and treating with networking data that said those are the limits that we have in iteratively weighted least squares. What are the limitations out of it? And I think that's the question. They try to say, how good are we in making linear regression models and see how far we can tune the applicability of these methods. And I think this is the key. The key is to go and see what are the limits of those methods and go one step beyond.
Thank you.
So just to get it clarified, the main message that I took from what you just said is that it's important to do feature extraction and feature engineering of the data such that the input to the machine learning method that comes after fits the mathematical properties. Okay. That's basically what you mean, right? Or do you mean something else?
I mean that actually this end-to-end view is nice when everything works and there's a generalization which has been proven. If you have a limitation of that method, you will still have to spend time in processing, pre-processing your data, so the feature and extract engineering and the task regression classification. So we are far from there to have modules that can be reused if people from networking do my traffic analysis, do my traffic prediction. We are not ready at that level. I think there is still a cycle that needs to be done in terms of research, in terms of best combination of which properties of the data needs to be injected for the feature extraction being done by neural networks. And then the classification and regression, I would say the regression poses more challenges than classification in that sense. Because actually the regression, as is shown here, it depends. We have one thing that we didn't discuss today, noise. How do you model the noise that you have in your system? The epsilon. Everything is related to epsilon. The problem is error corrections, is epsilon. If you have actually a good way of modeling how the errors behave, we could also have the right regression analysis techniques that we can embed into those neural networks and give then modules that could be used by people out of networking. You cannot do this nowadays. Learning weights is extremely difficult in weighted least squares. And it's even get more involved in GLS and IRLS. So I think that's a message that I want to bring. We're not at that stage of I would say, to fulfill the needs that what we can see out of networks today.
Okay, other questions?
But I just want to be clear. This is if you want really to have machine learning at the forwarding and control level. This was the perspective towards that was to be clear on that. To be clear on that.
Thank you for that analysis on distributed analysis. I just had a basic question. Were you assuming that in that analysis, you assuming that the models are homogeneous across the distribution, or is it does it play any role that they may be different type of models which are distributed? Thank you.
Well, okay. Let me do this one thing for you, because I prepare a slide for that, because I knew the question would come. But the problem is I have to go fast. I knew the question would come, so I think that your answer is as follows. The answer is here, is I do not necessarily believe that you would have an homogeneity of applicability of the models. And I don't think that when I speak about distributed, I'm hiding probably the major difficulty that you are going to face. It's not about centralized learning or being a distributed federated data when everyone exchanges all the data. The question is really to have decentralized learning, because what you need to learn and the technique that needs to apply at certain parts of the network might not necessarily be the same as the others. And this is what I call decentralized learning. When you don't exchange the data, but you exchange what you have learned and how you have been doing it. And I knew that question would come in, so I kept it for, I would say, the answers. And
It's okay.
But that's actually the point. The point is, I spoke about modules, but I wanted to say we are not even at the level where we could say, use that combination of data processing, feature identification, and then the regression task that comes after, at that level to say how to decentralize them. And I think it comes step by step. What I think a lot, and if you take the complexity of the learning task we have, is on modularity. We have to go back to people who speak about Baran. I should go back to Dijkstra. He's the one that introduces modularity in the way to process complex problems. It's a bit of the same thing. If you expect that you're going to have a package that's going to be able to learn the very nitty, I would say, specifics of each of the learning tasks you have in networks, I think it's probably something also to be a bit aware of, that it might also require sort of modularization at certain levels. And I think that is part of the answer too. Somewhere it goes together how to make a system scalable, because incremental updates is typically how the networks have been able to keep their scaling. It's probably also going to be a similar concept in learning.
Okay, thank you, Dimitri. Laurent?
There was one point in your conclusion slide, so you have to cut down. That puzzled me a bit, because you were comparing with a more centralized approach versus, distributed systems constraints, and you mentioned that they have the ability to perform offline versus the distributed environment where we are more online. But I don't really get why necessarily, why they have this degree of freedom. They also need to serve at online, runtime. So why this distinction?
Okay, no, but I will make it clear, because it's a word that people are using, but I don't even necessarily like it. I prefer the terms batch and near real time, because actually what it means, there is a meaning between near real time. It is batch and near real time versus real time in stream basis. That's the difference. Is that here what has happened is you still have the possibility to run different processes in parallel quite fast and still keep the correctness of the answer of these different processes. So you have a target, not just in terms of time, but also in terms of precision of the answer you have. You do not have any more this flexibility on doing this online. Typically, what you have is you have a notion of being required to run this as actually the input comes in, but also in terms of correctness that that's going to happen. In a centralized system, typically, you're not going to have this possibility of being more flexible in terms of decoupling the arrival of the data versus the timing at which you need to produce an answer. It doesn't necessarily mean that you would produce an answer, on an indefinite time. It means that you have more flexibility on the correctness versus production of the
so it's more the decoupling of
right.
ROI.
But because you have to be clear, if you count the delay as being a composition of queuing, scheduling, propagation, and transmission delay, basically, and propagation and processing queuing is typically the major components of time in the system. And if you want to have a delay prediction, well, actually, you start to have a big issue because you will start to have situations where even what you learn becomes actually out of date compared to the usability of that information. For traffic analysis, a bit of the same thing. That was a bit our issue that we had in the previous generation of techniques. It worked fine to update the parameters of a fitted time series model. But you need almost to have a large amount of resources in order to keep these updates of parameters available. Making them, I would say, available on each of the nodes was a non-starter from the beginning. People were telling us, you're not going to have a mainframe next to each router in order for you to analyze online the parameters of a time series. That was a bit the trade-off, in the sense, yes, indeed, what you want to have is a notion of real-time or near-real-time processing, but keeping actually the trade-off fast, as was said before, but also accuracy being real. You have to keep in mind next to this, and I think that wasn't, I didn't spend a lot of time on this, but typically what you have as flexibility when you're in a conventional system is not necessarily network management systems. It can also be systems that you use to analyze physical phenomena. You have much more flexibility in determining the decomposition of a given task, because actually it's driven by learning objective and performance, while in systems like we are dealing with internet, the decomposition itself is constrained by the system design. I will give you an example. If I need, at certain point in time, to a fraction of a link state update information, I need to infer into the database, you have a huge impact in terms of how the system behaves. Typically, you do not have this sort of constraints if you have this flexibility, and it's a flexibility, to abstract the system in your way you want, have the representation of this information at the management level or whatever, I would say, offline system you can put in place. That was the same for us when we were starting to determine how this time series analysis affects actually the forwarding plane. You need to hook on the forwarding information basis. When you look a bit on I would say, the sizes of those today, even if you introduce a probe on it, you are perturbing actually the system itself. So there are elements that you have to keep into considerations that happen. When you are making measurement about the system, you have a certain perturbation of the functioning of that system. You try to be, of course, as seamless as possible, which is typically considerations that you do not have when you speak about network management and maintenance. You always assume that the data would be available and you will send back the decision. Well, it's not how it works, because you need to tap that information from points into the system, which are not easily accessible, neither for the network management or whatever machine learning engine you want to drop onto your system. That's a message that I want to bring. Next to this, in distributed network systems, the value will come in being on path, not just by, as I said, downsizing what you have on a network management system on each node. This is not what it's trying to say. This is an online processing of the data you have at the control and traffic level. Okay, that's just to make the point clear.
Thank you, Dimitri. Let's thank Dimitri again.
Thanks.
Thanks a lot.